Alright, this video is going to be for Chapter 5, which is about Ethernet, the Ethernet protocol that works at the bottom two layers of your OSI model, the data link layer and the physical layer. So, we'll go ahead and get it started. So, we're going to talk about how Ethernet works in terms of switches. We're going to talk about the address resolution protocol that has to do with Ethernet and just the Ethernet protocol itself. Okay. So that's just what we should be able to do after that. Alright, so Ethernet is defined by data link layer protocols. You've got the 802.2 protocol, which is the LLC, or logical link control sublayer. It's important to know that that's the sublayer that communicates with the upper layer protocols, and it's also implemented by software. Okay, the MAC sublayer below the 802.3 is hardware implemented. Okay, it has to do with the media that's being used and the handoff from the data link layer to the physical layer. We discussed that a little bit in the previous chapter. What you see is kind of what you get here. It's the most widely used LAN technology. Ethernet operates in the data link layer and the physical layer. Covers the 802.2 and 802.3 standards. Operates from anywhere from 10, 100, 1,000, 10,000, 40,000, 100,000 megabits per second, which equals 100 gigabits per second. Okay. Defines layer 2 protocols and layer 1 technologies, broken up into two parts: the logical link control and the MAC sublayers. So we'll go down once again. We've seen this before, so you can see how the 802.2 covers the LLC sublayer. You've got Ethernet, fast Ethernet, gigabit Ethernet, all in the MAC sublayer, which is kind of how the data link layer, not kind of, it is how the data link layer communicates with the physical layer. So those are the different standards you have at the MAC sublayer. Okay. So you have the primary responsibilities for the MAC sublayer: data encapsulation and media access control. And remember, media is the cabling or how our data is being transferred. You have the physical signaling sublayer and the physical medium. You kind of don't need to know how this is all broken down. You just have some standards here for coax cabling, for unshielded twisted pair, so on and so forth. What is important there is to know how fast each one of these is going. That's what that number at the front means. So you've got 10 base, 100 base, 1000 base. That just means megabits per second. That's how fast it'll carry the data. Other than that, you're not really going to see that come up on your testing materials. Okay. The size of an Ethernet 2 frame. Okay, that's going to be important. So you've got an 8-byte. Remember, there's 8 bits in a byte. Okay, so that's an 8-byte preamble, not an 8-bit preamble. You got a 6-bit destination address, 6-bit source address. You've got the type, which contains the type of upper layer protocol being used, whether it's IPv4, IPv6, or even ARP, which we'll talk about a little bit later. The code for IPv4, I don't think you need to know this, but the IPv4 code is 0x800. For IPv6 is 0x86DD, and for ARP it's 0x806. You'll see that in your readings if you go ahead and take a look at the NetAcad course. Okay, your data can be anywhere from 46 to 1500 bytes. Okay, that's just the range that you get for an Ethernet 2 frame. All right. And the last part is the frame check sequence. This is where the CRC calculation happens and checks your frame against the CRC code that is embedded here and makes sure the frame isn't corrupted. Okay. So we go on to the next. So you do want to know the minimum size for your Ethernet frame and the maximum size. So 64 bits and 1518 bits. All right, that's going to be important, probably a test question. Anything lower than 64 bits is going to be called a runt or a collision frame, and if your node receives a frame that is lower than that, it's going to discard it. Same thing with a jumbo frame or a baby giant. It's too big, your node knows it's too big, so it's going to discard that frame, figuring that something has happened to it along the way from the source to the destination. So know those terms, runt, baby giant, jumbo, and know that if it is below that 64 bytes or above that 1518, the frame is going to be discarded. Okay. MAC address and hexadecimal. So hexadecimal values we'll have to talk about a little bit here. Probably have to talk about them a little more in class. But basically with hex, and we haven't even talked about binary that much yet, but at some point we will. You got your normal decimal values, 0 through 15. Okay. Your hexadecimal values go from 0 through 15 as well, except they don't use the double-digit numbers. Okay, you go from 0 to F, so it's going to be 0, 1, 2, 3, 4, all the way up to 9. 10 is A, 11 is B, 12 is C, 13 D, 14 E, 15 F. Okay, so that's how you get your value there, which is pretty simple in this situation. But when you get to different situations, then it does become a little more complicated. All right. Binary we'll talk about in class and how to convert that. Basically, these binary values all do line up with the numbers you see to the left and right. There's just a certain way you break them down, and we'll talk about that later. The hex values, if you just want to convert them to decimal, it's even somewhat easy if you just want to go from hexadecimal to decimal. So we got two digits here for our hexadecimal values, and here's how you're going to compute those. Anything in the second place or the first place here, so we've got F0 for instance. I'll take this as example, F0. You're going to take that F, and whatever value that is, you're going to multiply it by 16. Okay? After you multiply that by 16, you add whatever the value of the second digit is, and you'll get your number. So this F, if you multiply by 16, that would be 15 times 16, and I believe you should get 240. Let me go ahead and calculate. All right, so let me bring the calculator in, and we go 15 times 16 equals 240. So F, which is 15 times 16, okay, equals 240. There's a 0 here, so we don't add anything to it. All right, so if we take that 240 we just determined that this first F value is, we add the second F value down here, that's another 15, you get 255. Okay, let's take a look at this value here, 202. We've got a C, which equals 12. So if we go 12 times 16, we get 192, which we can see with the C0 actually up here, it equals 192. A is going to be 10, so 192 plus 10, I'm not going to do that on the calculator, we can do it on our head. That gives us 202. So you can convert hex to decimal that way, and we'll again talk about the binary conversion a bit later. So there is that. All right, we'll go ahead and move on. Your MAC address, okay, your MAC address. So your media access control address is made up of those hexadecimal values, okay. So a hexadecimal value for your MAC address would be 00602F 3A06BC. Okay, there's 48 bits in total in your MAC addresses. Okay, so basically each 2 digits of your MAC address is 8 bits. That's how you get this 48-bit binary value. Okay, so each 2 digits here, 8 bits. How can we tell? If we go back to our other chart that we saw, there are 8 digits in binary. Those each a bit. So there's 8 of them. That's where you get the 8 bits from. All right. So each one of these is 8 bits. 6 times 8 is 48. We get the 48. Anyhow, you have 2 parts of your MAC address. You have your organizationally unique identifier, which is the first 6 digits or first 24 bits. Those are assigned by the IEEE to a vendor, and the vendor uses that for the products they manufacture. So their products will have this first set of 24 bits on a lot of their devices, and then they themselves will assign a value for the last 24 bits to identify each individual product they make. So the example we have here is Cisco would have been assigned this organizationally unique identifier. They'd put that on their devices, and then on the different devices they make, to separate them from each other, they'd assign these last 24 bits, or last 3, I guess, hexadecimal values to the MAC address. So that's how MAC addresses are made. Okay. Just have an example of frame forwarding here. If you're basically broadcasting the frame, you send it out on the network. Everyone the frame is not addressed to will discard it. The person that it is addressed to will claim it as their own. So it's addressed to CCC. The station with the C MAC address claims it. And this is what happens when the station receives that frame and it does match or doesn't match. If there's no match, the device discards the frame. If there is a match, it goes ahead and sends it up the OSI layers to de-encapsulate the information. So that's what you have here. You've got different ways of representing MAC addresses. You can use the dash, you can use colons separated at every 2 digits, you can use a period separated at every 4 digits. Those are all the different ways you can write your MAC address out. So if you see any one of these formats, that can represent a MAC address. Okay. We've got a couple different ways the MAC address can be, the destination address can be written in your frame. So unicast is normal. This is what we've pretty much discussed so far. You have a certain destination and certain source. All right. So that frame gets passed along to the source, to the destination, and then he's the only one who receives it. Okay. So there is unicast. Simple. Destination receives the frame as it should. All right. A broadcast, if you are broadcasting the frame to everyone on the network and you want them all to process it, okay, a broadcasted frame, each end device is going to accept that frame and process it, okay. Depending on what's in the frame, the device still may not send it all the way up the layers of the OSI model and may not reply to it, but each device is going to accept it and broadcast it. And what's important to know here is the destination MAC address of a broadcast is going to be FFFFF, all Fs. Okay, that's going to be important when we talk about ARP requests, because ARP requests are basically going to have that destination MAC address. Okay, then we have multicast. Multicast is from one station to a certain group. Okay, that specific group is predefined, and how you set that up we get into a bit later. But that is a predefined group indicated by this destination IP over here. Okay, that's what the multicast group is designated by. For us, in terms of the MAC address, the first 3 hexadecimal values here, 01005E, that indicates that this is a multicast frame. Okay, so that's going to be important to remember. 01005E is for multicast. This last value is calculated based on the host bits of this address over here. So you've got 200 in the host bits, and C8 actually is 200. So it's going to calculate and make that match basically. Okay, so that 200, if you take C, that's 12 times 16, which is 192, plus 8, that's 200. Okay, so we'll move on from there and talk about how LAN switches work in terms of Ethernet and ARP control, actually frame forwarding methods, I believe, in this section. Okay, switches are going to have MAC address tables. All right. An Ethernet switch is a layer 2 device. There are layer 3 switches that we talk about a little later on. Uses MAC addresses to make forwarding decisions. The MAC address table is sometimes referred to as the CAM table or content addressable memory table. And we'll talk about how that memory is stored inside specific switches in just a bit. Okay, so learning MAC addresses. The main thing to take from this is switches learn MAC addresses based on source MAC, not destination. Okay, because it may not know. The switch may not know who accepts and replies to the frame. It just makes more sense for it to take the source MAC and add that to the table. So you've got this packet here, or this frame, that's being sent to 0D, which is this computer D over here, and the source is A. It's going to send this frame up into port 1 on the switch. Okay, and we're going to say this is just a 4-port switch. Okay. And as it's sent into the switch looks at the source MAC address and says, okay, port 1 belongs to the MAC address 00-0A. So I'm going to put that in my table so I know exactly who's connected to port 1. Okay. It doesn't have the MAC address 000-0D in its MAC address table. So since it doesn't know, it's just going to pour all of those frames out, all ports other than 1. Okay, or if it were to learn more MAC addresses, let's say it knew the MAC address of 0B over here, number B or letter B. If it knew this MAC address on port 2, it would not send out port 2. It basically would send out that frame on all unknown ports, to try to get a successful reply from whoever the frame is addressed to. So it broadcasts the frame if that MAC address is not in the MAC address table out all unknown ports. But if a port is in the MAC address table and it knows that 000B is on port 2, then this wouldn't happen, this communication. Okay, it would just send a 3 and 4. So I hope that's clear. Alright, so it goes out and station D sees that this is my MAC address. Okay, I'm going to reply. As it sends the reply back, the switch receives its frame with the source for station D, adds that to the MAC address table as it receives the frame and sees that source address. So now it knows the MAC addresses for both ports 1 and 4 there. So that's how your switch is going to learn and build its MAC address table. Alright, since it already knows the MAC address for station A over here, it can go ahead and just send it through to station A. That's how switches are smarter than hubs. It's going to keep that MAC address table, cause less network congestion, because it's only going to forward that frame to the appropriate port. Alright, if the port's MAC address is in the MAC address table. Okay. Let's see. It sends another one to D. Now that it knows D, it won't come out the other ones. Since it's in the MAC address table, it just goes in 1, out 4. That's how it would go. Let's see if the next slide says what I want to say. A switch can have, yes, multiple MAC addresses associated with a single port. If there is another switch plugged into a port on a switch, that switch is going to have multiple MAC addresses associated with it. Okay, so let's say I have a switch here with 3 different stations, okay, with 3 different addresses to port 3. All 3 of those addresses will be eventually associated with port 3 if I were to have a switch here instead of a desktop PC. Okay, so you can have multiple MAC addresses on the same port. All right. And I believe we talked about this a little bit in class. I think we have. When the destination IP address is on a different network, the Ethernet the destination MAC address is actually the destination of the default gateway, or the way to get to that remote network. So that's what's going to happen. Your frame's going to have the destination MAC address of your default gateway if your destination IP address is on a remote network. Okay. So we have switch forwarding methods. We've got store and forward, which is used most often because there really isn't that much delay in using a store and forward versus cut through, and it's going to be more reliable because store and forward receives the entire frame, actually takes a look at the CRC value, makes sure the frame is valid, then sends it on. If the frame's not valid, it's going to just drop it. So store and forward is a more reliable, error-free technique. Okay, and the switch will do some of that CRC for you. Cut through is going to forward the switch either as fast as it can in one method, or another method it's going to make sure that it's not a runt, and then send it forward as fast as it can. So there's two different cut through methods. Store and forward is what it is. It takes the entire frame, calculates the CRC, and if it's valid, moves it on. Our two different cut-through methods are fast-forward switching and fragment-free switching. Fast-forward is going to read just enough of the frame to know where this packet, or the frame, needs to go, and then send it. Okay, that's all it's going to do. It's fast-forward switching. All right, so it reads just enough to read the destination address of the frame, and then sends it on its way. So that's how cut through. That is the typical cut through method of switching. You also have fragment free. Fragment free stores just the first 64 bytes of the frame, not bits, bytes, because we're talking storage. Stores the first 64 bytes of the frame before forwarding. And we looked at earlier, from talking about runts and giants and collision frames, that anything below 64 bytes is considered a runt. So that's why it stores those 64 bytes, to make sure you're not sending on a runt frame onto the network. Okay. So how switches store MAC address tables and how they store things that they need to remember in their memory. They've got two different methods. Each port can have memory associated with that particular port. So each port will have a certain amount of MAC addresses it can store. And when that runs out, then it'll have to start purging some of those MAC addresses. You've also got shared memory, in which there's a common bank, and as different ports need to access that memory, they do. So if one port only has one MAC address associated with it, another port has 10, or something to that effect, they'll be able to share that memory. The one with 10 won't run out of memory because it only has a certain allocated amount for that individual port. It can go ahead and dip into the well and use as much as it needs to, as long as the other ports aren't using too much memory as well. So you've got port-based, where it's saved. You have memory assigned to just each port, or shared memory where all the ports share. Okay, simple as that. Alright, we got switch port settings. You've got full duplex and half duplex, which we've talked about. The ability to send and receive at the same time versus only send. Okay, so you've got duplex settings and speed settings that we can set up on our devices, on our switches. We will do that in a lab. You do that from an interface configuration mode, so you'd have to be like on Fast Ethernet 1, interface Fast Ethernet 1. You'd say duplex full, duplex half. You'd say speed full, speed half. You can also have it auto-sense the duplex mode, or auto-sense the maximum speed. So those are options that we'll see as well as we program our switches in class. Okay. So duplex and speed settings. If you're only on half duplex and the other is on full duplex, the full duplex one's always going to be trying to send and receive simultaneously, and you're going to end up with collisions for the guy on half duplex because he's only able to hear or listen one at a time. So, I mean, you want to make sure your duplex modes are matching. You can also go to an auto duplex and let it automatically detect what the other device is using and negotiate from there. Okay, so you don't want those collisions to happen, of course. Auto-MDIX is going to detect automatically whether you need a straight through or crossover cable. We talked about this a little in class when we built our cables, that even though we need to know when a straight through or crossover cable is appropriate, if a device has Auto-MDIX or auto sensing enabled, it will just sense what type of cord you're using and send and receive without issue. It can go ahead and negotiate that cord no matter what kind of cord it is. So it'll correct it if you have a crossover where you should have a straight through, or you have a straight through when you should have a crossover. Okay. And we move forward. The last section, ARP Address Resolution Protocol. Okay, so after this section, we will compare the roles of MAC addresses and the IP address table, describe ARP, explain how ARP impacts the network and host performance. So here we go. We've talked about how we have two primary addresses, the physical address or MAC address and the logical address or IP address for your device. The IP address being your remote address, so to speak, and your MAC address being your local physical address. Okay. When we're sending packets along, the IP address doesn't change, and the MAC address changes from hop to hop. All right. But we need a way for our devices to know the MAC address or the destination MAC address it's trying to send to. It may know the destination IP, and it will through either the DNS server or other means, but we need to know the MAC address as well. That's where ARP comes in. Okay, so we've got host H1 needing to send information to H4 over here. All right, it doesn't know the MAC address of that device that has the IP 192.168.1.7. All right, so ARP is the function you're going to use to learn that MAC address. All right, your ARP table is used to find the MAC address that is mapped to a destination IPv4 address, or the ARP process is. If the destination IPv4 address is on the same network as the source IPv4 address, so it's a local network, the device will search the ARP table for the destination IPv4 address. Okay, so this is an ARP table that is stored on your end device on your router. Okay, we're talking end devices right now in the presentation. If the destination IPv4 address is on a different network, the device will search the IPv4 for the IPv4 address of the default gateway. Also, it will search the ARP table. I shouldn't say also. It will search the ARP table. That's what it's searching for, the IPv4 address of the default gateway. Okay, so it is searching the ARP table for the IPv4 address of the default gateway. If that's not in the ARP table, the device, if it locates the address, it's used as the destination MAC address for the frame. If no entry is found after looking up in the ARP table for either the device on the same network or the default gateway, then an ARP request is sent. So you could be sending an ARP request to either find the destination device on your same network or your default gateway's MAC address. Okay. So your ARP request is sent when a device needs to associate, it needs a MAC address associated with an IPv4 address, and it does not have it in its ARP table. All right. So the target IPv4 address requires a corresponding MAC address. The target MAC address is unknown and will be empty in the ARP request message. All right. So the ARP request is encapsulated using this header information you see below, that the destination MAC address is a broadcast. So that's going to be all Fs. That's what you have for a broadcast MAC address, is all Fs. All right. The source MAC address is the sender's MAC address, and then the type field. We saw the different fields of your Ethernet frame earlier on in the video, very early on in the video. That's going to have a field type of 0x806, and that's an ARP message. All right, your ARP reply, the device with the target IPv4 address in the ARP request will respond with an ARP reply. ARP reply message includes the sender's IPv4 address, the sender's MAC address, which is what the ARP request was asking for. Okay, so this is the MAC address of the sender, the MAC address needed by the sender of the ARP request. That's kind of confusing because we're saying that the sender is the person replying to the ARP request here, and the sender they're referring to here is the person who sent the ARP request in the first place. So I know it says sender here twice. Don't let that confuse you. Those are two different stations, the one replying and the one who requested initially. Okay. The ARP reply is encapsulated in Ethernet frame using the following header information. The destination MAC address is the MAC address of the initial sender. The source MAC address, this is the sender of the ARP replies MAC address, and the same ARP type is there. Okay, so you got that for the local network. For a remote network, you're going to look for the IP of you're going to send the ARP request, and you're going to get a reply from the default gateway, because that's what you're looking for. When the destination IPv4 address is not on the same network as the IPv4 address of the source needs to send the frame to its default gateway. The source checks the ARP table for an entry for the default gateway. If there is none, it's going to use that same ARP process to find the MAC address of the default gateway. So that is what's going to happen there. And we move forward. Removing entries from our ARP table. Before we even talk about sending the request, I don't think we actually go through the command actually of sending. We don't send ARP requests. That's right. So we won't see the command for sending an ARP request. It's an automatic process. So removing entries from an ARP table. There is an ARP cache timer which removes ARP entries that have not been used for a specific period of time. Okay. There's also a command to remove all or some of the entries in the ARP table. We'll talk about those in the lab, and that's going to be a clear ARP or a clear IP ARP that we'll use. So you'll see that. You can see this device down here is set to remove ARP entries in 2 minutes. Okay. If you want to show your ARP table, you've got to show IP ARP that you will use. If you're on a router, okay. If you're on a host device and you're in the command prompt, you've got a ARP --A that will show your ARP table. Okay. ARP issues. The ARP can flood your network with traffic, especially if devices power on at the same time. They're all trying to discover who their neighbors are and how to contact them. So that can cause congestion in your network. And also you have people who could ARP spoof by replying to a ARP request saying that they have the MAC you're looking for, even though they don't. So they want to intercept your traffic. This is the type of man-in-the-middle attack that you would have. So ARP spoofing would be somebody trying to pretend that they are some device in your network that they aren't. And that's the end of our Chapter 5 video. So that's it. We will perform some labs in class to show how the ARP process works and how to configure our switches. All right.